Hey there, welcome to another session of math problem solving. And this will be looking at the spider and the fly problem. Let's get started. So we have a rectangular room, so three-dimensional rectangular room, which means it's basically a cuboid, measuring 30 feet across, 12 feet tall and 12 feet wide. There's a spider in the middle of one of the end walls. Going to denote this particular thing as A, 1 foot from the ceiling, so just 1 foot below the ceiling. A fly in the middle of the opposite wall, 1 foot from the floor, that's point B. Now this is a little hard to imagine, so let's put a diagram here to help us understand. So as you can see, it's a cuboid, a rectangular prism, a rectangular room, however you want to call it, 30 feet across. And on both sides of the wall, the left and the right has point A, which is basically the spider, 1 feet from the ceiling, just 1 feet from the top. And B is on the left-hand side wall, 1 feet from the floor. Now the question is, what is the shortest distance the spider must crawl in order to reach the fly? Let's assume that point B, where the fly is stationary. The fly doesn't move while the spider actually comes in, captures it. Now this is not a very simple problem because it's three-dimensional, a little hard to kind of visualize, but let's try our best here. So one of the mathematical problem solving strategy is to try out different options and see what is the best way in which it can work out. For instance, the way I would look at it is to say, how many different surfaces will the spider have to crawl through to go from point A to point B. For example, the simplest one, if I were to take this and say, okay, I'm just going to go through 3 different surfaces. That's the minimum number to go from A to B. Okay, so imagine literally that he is climbing down, vertically down, reaches the floor, crawls exactly across the floor, and then climbs up 1 feet to catch the fly. This means he's using only 3 different surfaces of the room. The other 3 surfaces, which is the front, the back, and the top, is untouched. The spider just doesn't go to any of these 3. If you can visualize this, then you know that the distance is nothing but the distance that he travels down on the right-hand side wall, which is 11 feet, the distance across the floor, which is 30 feet, and the distance up on the left-hand side wall, which is 1 feet. Putting all this together, it's 42 feet. And this looks like a fair enough answer. Definitely it's correct. But is this the shortest? We've got to try something else for that. So is it possible for the spider to travel to 4 different surfaces? So for this, we're still at 3 different surfaces. Probably another way to look at it is, instead of coming to the floor, is it possible for him to go from the back wall altogether? So the floor is there, the front wall is just falling flat. This is called the net of a cuboid, as you can imagine. So he's basically traveling, the spider is traveling across on the right hand side wall, across on the back side of this room, and across on the left hand side wall to reach B. So to find this distance, what we need is to find the horizontal distance, which, as you can see here, is 6 plus 30 plus 6. The vertical distance, which in this case is literally just from where A is to where B is, and then use Pythagoras to basically say the distance is going to be the square root of the square of the horizontal and the square of the vertical distance put together. So in which case it's 42 square plus 10 square, square root of that being 43.174. As you can see, this is a little longer than the other one. So we still are using 3 surfaces, but unlike case number 1 where it was literally vertical all the way and using the floor, this is a little bit of an oblique path, but using the back side of the wall. Let's go to the third option. In this case, we're going to use 4 different sides of the wall, which means he's going to move across the right hand side wall. He's going to move across on the back side of the room, and then he's going to hit the floor. He's going to walk across the floor and then walk across the right hand side wall, the left hand side wall, to reach B. So in this case, what do you think is going to be the horizontal distance, and what do you think is going to be the vertical distance? So the horizontal distance is basically the 6 that he has to travel on the right hand side wall, and then the 30 that he anyway has to travel. I know it's kind of oblique, but he has to cross that horizontal distance, which is 30. But for the last part, he just needs to climb up by 1, and therefore it is 37. But for the vertical distance here, it's a little bit of a toughie, because he needs to travel 11 down, because he's reaching the floor. Remember, he's getting to the floor, so it means he goes all the way down to the floor and then climbs up by 1. So the vertical distance here is basically 11 plus 6, which is 17. So the distance by applying Pythagoras theorem is going to be 37 square plus 17 square, which is 43.178. Okay, let's go to the fourth possible option. In this case, he gets to travel across 5 different surfaces. So this looks like the most convoluted one, but this is the answer. So he travels across A, gets to the ceiling, travels across the ceiling, then travels across the back, getting to the floor, and then finally reaching B. So the horizontal distance in this case is just 1 on the top, 30 across, and 1 in the bottom. The vertical distance is the 6 that he needs to travel to, looking at the net here, right? So the 6 that he needs to cross to get to the top, then the 12 that he needs to move down all the way from top to bottom, and then 6 again to get to the point B. So here it's 32 square plus 24 square. Square root of that would be 40, which would be the answer. Now, the best way to understand this problem is to see if you can build a rectangular cardboard, mark the points A and B. You could take a regular shoebox and actually try and chart the path for each of these 4, both inside as well as outside, internally and externally, for you to understand this problem at a deeper level. And hopefully you'll be able to get why 3-dimensional problems are so very complicated, because it's very, very hard to figure it out. But one key technique that I want you to remember as a result of this problem solving is to say that 3-dimensional figures could be understood better when you actually turn them into a 2-dimensional net. And hopefully that helps you understand and solve the problem much better. If you like the video, please do like, subscribe, and share, and I'll see you in the next video. Thank you so much.